Let us begin very gently with a familiar kind of situation. Imagine a help desk in a company. Calls come in during the day. Sometimes there is a brief quiet period, and then 2 calls arrive not very far apart. Then perhaps another calm stretch follows. If we stand back and watch for long enough, we begin to feel that there is some general pace to the arrivals. Not an exact script, not a timetable, but a pace. A kind of average rhythm. Or imagine a production line where small defects appear from time to time. Not every item is defective. Most are fine. But occasionally a defect appears. Again, not in a perfectly regular pattern, but with some average tendency. Or think of accidents at an intersection, emails arriving in an inbox during an hour, or faults appearing in a machine over the course of a week. All of these examples have something in common. We are counting events. The events are often relatively infrequent compared with the amount of time or space we are watching. And what we want to understand is not so much the exact count in the next short interval, but the underlying pace at which such events tend to occur. That is the heart of today's topic, estimating Poisson rates. In common language, we are trying to estimate the average tempo of rare random events. It is worth pausing on that phrase, average tempo, because it already captures the spirit of the whole topic. We are not trying to predict the future with certainty. We are not trying to say exactly how many calls will arrive tomorrow at 10 in the morning, or exactly how many defects will appear on the next 100 meters of material, or exactly how many emails will arrive in the next half hour. That would be asking for too much. Random systems do not usually offer that kind of precision. Instead, we are trying to describe the deeper rhythm underneath the visible randomness. We are trying to say something like this: on average, this kind of event tends to happen at such and such a pace. A common analogy may help here. Imagine lying indoors during a light rain and listening to raindrops on the roof. You do not expect the drops to land with perfect regularity, like the ticking of a clock. Some moments feel slightly busier, some slightly quieter. But over time you begin to sense a tempo. You begin to feel the typical pace of the drops. Not the exact next sound, but the general rhythm. Estimating a Poisson rate is very much like that. We listen to the random arrivals, and from what we hear, we try to describe the average tempo. Let us pause and reflect on why this matters. This topic appears very often in university statistics because it sits at a beautiful meeting point between theory and application. On the theoretical side, it introduces one of the most important models for count. On the applied side, it connects directly to real problems in engineering, medicine, operations research, quality control, traffic analysis, insurance, and many other areas. Whenever someone is counting occurrences over time, over space, over area, or over some measure of exposure, this model often enters a conversation. So, although the mathematics behind it can be formal, the intuition is rooted in very ordinary observations from life and work. Now let us turn to the Poisson model itself, but slowly and without formal symbolism. The basic idea is that events happen one by one. They occur randomly rather than according to a rigid schedule. And the main feature we care about is the average rate at which they occur over a unit of time or a unit of space. That last phrase is central, average rate per unit. The parameter in the Poisson setting is not the future count itself. It is the typical pace. It is the average number of events we expect relative to a chosen unit of observation. So if we speak about calls per hour, the parameter describes the average pace of calls in 1 hour. If we speak about defects per meter, it describes the average pace of defects along 1 meter of material. If we speak about failures per week, it describes the typical pace of failures in a week. If we speak about disease cases per 1,000 people, it describes the average pace relative to their population size. It is worth repeating, the parameter is a pace, not a promise. It is a long-run tendency, not a guarantee about any single short period. This distinction matters because students often first meet a count model and unconsciously attach too much certainty to the parameter. They think that if the estimated rate is, say, 4 per hour, then 4 will somehow be the expected visible outcome in each hour in a strong sense. But that is not how random counts behave. A fixed rate still allows fluctuation. 1 hour may bring 1 event. Another may bring 6. Another may bring none at all. The rate is the stable background tendency, while the observed counts move around it. Let us now ask the natural question. If the parameter is this average pace, how should we estimate it from data? The answer is wonderfully intuitive. If events occur at a stable average pace, then the observed average count is the natural estimate of that pace. That is the whole idea in its simplest form. If over many equal time intervals we observe counts, we average those count. If over one long observation window we count how many events occurred and divide by the size of the window, we get an estimate of the rate per unit. This feels almost too natural to be called a statistical estimator, and that is part of the beauty. Sometimes the best estimator is not strange or mysterious. Sometimes it is simply the quantity that expresses exactly what we mean by average pace. Suppose we observe calls arriving at a help desk over many hours. If the number of calls per hour has a roughly stable underlying rhythm, then the average number of calls across those hours is our natural estimate of the call rate. If we inspect a long strip of manufactured material and count defects, then the number of defects relative to the total length inspected gives us the natural estimate of the defect rate per meter. If we observe machine failures over several weeks, then the total number of failures divided by the total number of weeks gives us the natural estimate of the failure rate per week. The common pattern is simple. We do not just count events. We count events relative to exposure. That word exposure is extremely important in practice. 10 events in 1 hour and 10 events in 10 hours do not mean the same thing. The raw count is the same, but the pace is very different. In the first case, the system seems much busier. In the second case, the events are much more spread out. So what matters is not merely how many events occurred, but how much opportunity there was for events to occur. This is why rates are always tied to some unit of observation. Time, length, area, population size, machine hours, customer visits, and so on. The count alone is incomplete. The count must be interpreted together with the exposure. Let us pause and reflect, because this is one of the main practical lessons of the entire topic. When estimating a Poisson rate, we should almost never ask only how many events did we see. We should also ask over how much time, or over how much space, or over how much population did we see them. That is the real quantity of interest events relative to exposure. This becomes especially clear when exposures vary. Imagine one call center is observed for 1 hour and receives 10 calls. Another is observed for 10 hours and also receives 10 calls. A raw comparison of counts would suggest they are the same. But they are not the same from the point of view of rate. The first center appears to receive calls much faster. Or imagine one factory line is inspected over 100 meters and another over 1,000 meters, and both show the same number of defects. Again, the raw totals hide the real story. The rate per meter is different. Or think about disease cases across communities of different size. 10 cases in a small town and 10 cases in a large city do not indicate the same underlying pace of disease occurrence. We must normalize by population size or some related exposure measure. So a Poisson rate is always a normalized count. It is a count understood in relation to the observational scale. Now let us move a little deeper into the intuition of why the average-based estimator makes sense. When events are rare, short windows can be misleading. A quiet hour does not prove the rate is zero. A busy hour does not prove the system has become permanently intense. Randomness can make short stretches look very different from the long-run truth. This is why longer observation helps. If events are genuinely happening with some stable average pace, then short samples are noisy glimpses, while long samples are steadier summaries. Over time, random ups and downs begin to balance one another. The observed average starts to settle. In everyday language, the longer we listen to the raindrops, the better we grasp the average tempo. This is worth repeating because it is such an important statistical habit of mind. Rare events are noisy when viewed briefly. Stability emerges more clearly when we allow enough exposure. For that reason, in Poisson rate estimation, more time, more space, more population, or more observational opportunity usually gives us a better sense of the underlying rate. Not because randomness disappears, but because its short-run irregularities become less dominant relative to the full amount of data. You may notice that this idea sounds very close to many broader themes in statistics. We often seek a stable signal hidden inside variable observations. Here the signal is the rate and the variable observations are the realized counts. Let us pause and summarize what we have established so far. We began with counting problems such as calls, defects, accidents, emails, and cases of disease. We said that the Poisson viewpoint is appropriate when events happen one by one and somewhat randomly, and when we care about the average pace rather than a rigid schedule. We clarified that the parameter is not tomorrow's exact count, but the typical rate per unit of exposure. And we saw that the natural estimator is the observed average count relative to the amount of exposure. That is already the conceptual core. Now let us think more carefully about interpretation. Suppose we estimate a rate and obtain some value that feels reasonable for the system. What does that number mean? It means that if the underlying conditions remain similar, then over the long run the system tends to produce events at about that pace. It does not mean that every short interval must resemble that value closely. It does not remove randomness from the world. It gives us a summary of the system's average behavior. This is often where students need reassurance. They see fluctuation in the data and worry that the model has failed immediately. But fluctuation is not the enemy of the model. Fluctuation is part of what the model is meant to describe. A fixed rate can coexist with visibly changing counts from one interval to the next. That is not a contradiction. That is the central feature of random counting. So when we estimate a Poisson rate, we are not replacing uncertainty with certainty. We are organizing uncertainty around a stable central tendency. Let us say that again in a softer way. We are separating the surface movement from the deeper rhythm. The surface movement is the count we happen to observe in one particular window. The deeper rhythm is the average pace that governs the system over longer observation. And Poisson rate estimation is an attempt to uncover that deeper rhythm. Now, because we are speaking calmly and honestly, we should also mention a practical caution. The Poisson assumption does not always fit reality. Real systems are sometimes more bursty than the Poisson model suggests. Calls may cluster because of an outage. Emails may arrive in waves after a meeting ends. Accidents may become more common during bad weather. Defects may increase when a machine begins to wear down. Disease cases may cluster through local transmission. In all such situations, events are not arriving in a completely steady random way with one stable background pace. Sometimes the rate itself changes over time. Morning and afternoon may differ. Weekdays and weekends may differ. One production shift may differ from another. Seasons may matter. External shocks may matter. And sometimes events influence one another, directly or indirectly, which breaks the calm independence that the basic Poisson picture tries to capture. So it is important not to treat the model as a law of nature. It is a useful approximation. A disciplined lens. A mathematically elegant way to represent random counting when the assumptions are reasonable enough. This caution is not a reason to reject the model. It is a reason to use it thoughtfully. In many applications, the Poisson model works surprisingly well as a first description. In others, it needs modification. But even when it is not perfect, the idea of estimating average pace relative to exposure remains foundational. Let us pause and reflect again. A good model does not have to describe every wrinkle of reality. It has to capture the main structure clearly enough to be useful. In Poisson rate estimation, that main structure is the distinction between noisy observed counts and an underlying average rate. Now let us connect this gently to maximum likelihood, since that is often part of a university course. Students who have already seen maximum likelihood may wonder whether this average-based estimate is just an intuitive shortcut, or whether it also arises from a more formal statistical principle. The pleasing answer is that it agrees with the maximum likelihood way of thinking. Very informally, maximum likelihood asks which parameter value makes the observed data most plausible under the model. In the Poisson case, when one works through that logic, the result points to the same natural estimate, the observed average count, adjusted for exposure. This is one reason the estimator feels so satisfying. Intuition and formal method meet in the same place. The quantity that sounds right conceptually is also the quantity favored by the likelihood framework. That convergence is not always so simple in every statistical problem, but here it is especially elegant. The natural average-based estimate is not merely a rough guess. It is deeply tied to the structure of the model itself. It is worth repeating that point because it can strengthen intuition. When a model is well chosen, the most sensible descriptive summary often aligns with the formal estimation method. In Poisson rate estimation, average pace is not just a vague story. It is a statistically central quantity. Now let us spend a little time with the idea of rare events, because the Poisson model is so often introduced in that language. When people say rare events, they do not necessarily mean events that almost never happen. They usually mean events that occur individually and irregularly relative to the observational scale. Calls may not be extremely rare in an absolute sense, but they are still arrivals that happen one at a time. Defects may be uncommon compared with the number of items produced. Accidents may be infrequent compared with the total traffic passing through an intersection. The model becomes especially natural when the event count in a very small window is usually 0, occasionally 1, and only rarely more than 1. That picture supports the idea of separate, individual occurrences. But the main practical lesson for estimation remains the same whether the event is very rare or only moderately infrequent. We estimate the average rate by relating observed counts to exposure. And as the event becomes rarer, the need for sufficient observation becomes even stronger, because rare events generate more emptiness in short windows. If we look too briefly, we may see almost nothing, and that tells us little. If we watch longer, the average tempo becomes more visible. So again, more exposure does not remove randomness, but it gives randomness less power to mislead us. Let us now gather the entire story into one common thread. We begin with a system in which events occur one by one over time or space. We suspect that beneath the irregularity there is some stable average pace. We call that pace the rate. We observe counts over some amount of exposure. Then we estimate the rate by taking the observed count relative to the exposure, or by averaging counts across equal exposure windows. This estimate is meaningful because it describes the long-run tendency of the system, not the exact future outcome of any one short interval. It becomes more stable as we observe more exposure. It remains subject to randomness, because counts fluctuate even when the rate is fixed. And it works best when the Poisson assumptions are at least approximately reasonable, meaning events are not too strongly clustered and the rate is not shifting too wildly over the observation period. That is the structure. And now, before we finish, let us pause and reflect one last time in a very simple way. If you hear random drips on a roof, you can still speak of the average tempo. If you watch calls arrive, you can still speak of the average pace. If you count defects, failures, accidents, or emails, you can still look past the immediate irregularity and ask about the deeper rhythm. That deeper rhythm is what the Poisson rate is trying to capture. And estimating it is one of the most natural acts in statistics, to observe many uncertain outcomes and use the average behavior to describe an underlying tendency. So the core message of this topic is not complicated, even though it belongs to serious university statistics. Poisson rate estimation is about separating random count fluctuations from the deeper average rhythm of events. It is about not being fooled by a short burst or a short silence. It is about counting carefully, remembering exposure, and listening for the long-run tempo beneath the noise. And that is why the topic matters so much. It teaches a habit of mind that appears everywhere in statistics. Behind irregular observations there may still be a stable structure, and patient observation can help us estimate it. Let us end with a slow, unifying summary. In many real problems, events arrive one by one across time, space, or population. The exact timing is irregular, but there may still be an underlying average pace. The Poisson model gives us a language for that situation. Its parameter describes not an exact future count, but the long-run rate, the typical tempo, the deeper rhythm. To estimate that rhythm, we look at the observed counts and relate them to exposure. We think in terms of calls per hour, defects per meter, failures per week, or cases per population. We remember that raw counts alone are not enough. We remember that longer observation gives a steadier picture. We remember that fluctuation remains present even when the rate is fixed. And we remain cautious when real systems cluster or change over time. If all of that has settled in, even partially, then you already understand the heart of Poisson rate estimation. It is, at its core, the quiet art of hearing an average rhythm inside random events.